If it continues to deteriorate, those systems and more are at risk.
We lose our magnetic field for a significant period of time. Yeah, it would have catastrophic consequences.
Many people have come to depend on the Earth's magnetic field even without realizing it. Your phone is able to perform some of its basic functions because of it, like directing you while driving to your destination. However, a catastrophic event is threatening to render life-saving tasks like this impossible: the flipping of the Earth's poles. Why are the Earth's poles flipping? What are the consequences? And how can you cope with it? In this video, we dive into the Earth's poles flipping, which has many people worried as it's happening again. Thanks to science and technology, we have come to rely on many natural phenomena that are not apparent to the naked eye. The Earth's magnetic poles are an example, and this has a lot to do with the Earth's magnetic field. But what is the Earth's magnetic field and where did it come from? You probably know what a bar magnet acts like. Well, you can imagine a large bar of magnet inside the Earth, roughly aligned with the Earth's axis. Each end of the magnet lies relatively close to the geographic north and south poles. Really, there is just about 10 degrees difference. Earth's invisible magnetic field lines travel in a closed, continuous loop and are nearly vertical at each magnetic pole. The geographic north and south poles are where lines of longitude converge. The geographic north pole is located in the middle of the Arctic Ocean, and the geographic south pole is found in Antarctica. However, the magnetic poles are located where the magnetic lines of attraction enter Earth. The magnetic North Pole is also called the North Dipole and is currently found on Ellesmere Island in northern Canada. Note that we said currently found. When you follow a magnetic compass and it points north, what is happening is that it is aligning itself with Earth's magnetic field and points to the magnetic North Pole, not the geographic North Pole, which is actually about 310 miles or 500 kilometers away. But it doesn't end here. What is commonly known as the North Magnetic Pole is actually a South Magnetic Pole. Surprised or confused or both? Well, magnetic field sources are dipolar, meaning they have a north and south pole. And remember that for magnets, opposite poles, that is the north and south, attract, while other poles like north and north or south and south repel. So when your compass points north, in the actual sense, it is attracted to the South Magnetic Pole, which lies close to the geographic North Pole. And there is another fact about the Earth's magnetic poles which may surprise you again. They wander with time and are not fixed. For example, when British polar explorer James Clark Ross first identified the magnetic North Pole, it was located in the Boethus Peninsula in Canada's Nunavut territory in 1831. However, since then, the magnetic North Pole has been moving about 25 miles or 40 kilometers a year in a northwest direction. However, this movement is different from the magnetic poles flipping or swapping positions, which is way more severe. So where does the Earth's magnetic field come from? The Earth contains an iron core, so the magnetic field must come from there, right? Wrong. At high temperatures, metals lose their magnetic properties. The iron at the core of the Earth is extremely hot, so it is not responsible for the Earth's magnetic field. What you are looking for is geodynamo. This is basically what happens in a bicycle's dynamo light. When you pedal, the magnets in the dynamo begin to spin and create an electric current which helps to produce light. However, in the case of the Earth's magnetism, the reverse happens. That is because if you rotate an electric current, you'll generate a magnetic field. There are 4 conditions that the Earth meets that allow it to generate its own magnetic field through geodynamo. 1. It rotates fast enough. 2. Its interior contains a fluid medium. 3. The interior fluid has the ability to conduct electricity. And 4. The core has an internal source of energy that propels convection currents in the liquid interior. The generation of Earth's magnetic field happens deep within the Earth's interior in a layer called the outer core. The convective energy of the slow-moving molten iron is converted to electrical and magnetic energy. The magnetic field then induces electric currents, which in turn generate their own magnetic field, which induces more electric currents in a positive feedback loop. The Earth's magnetic field is very useful, and you literally owe your life to it. In fact, one of the reasons astronauts not adequately protected on Mars will perish is because of the magnetic field, or more accurately, lack of magnetic field. The magnetosphere, or protective magnetic bubble which is missing on Mars, shields us on Earth from harmful space weather like solar winds. The energy from the sun sustains us, but a side effect is solar winds which would have eroded our atmosphere and deprived you of the air that you breathe. The magnetosphere also blocks large quantities of particle radiation produced during coronal mass ejection or CME events. It also blocks another toxic stuff known as cosmic, which would have been raining down on us from deep space. Our wonderful magnetosphere repels harmful energy away from Earth and traps it in zones called the Van Allen radiation belts. These donut-shaped belts of radiation can swell when the sun's activity increases. Of course, while the magnetosphere provides an essential service, it is not 100% efficient, and mild breaches do occur. During very strong space solar winds or large CMEs, geomagnetic storms can penetrate the magnetosphere and cause widespread radio and power blackouts. It can also endanger astronauts and foul up Earth-orbiting satellites. But the effect is not always negative. In fact, one of them is actually a mesmerizingly beautiful thing. If you have watching the Northern Lights, also known as Aurora Borealis, or Southern Lights, also called Aurora Australis, on your bucket list, neither would happen if there is no disturbance in the Earth's magnetic field. It is the disturbance that sends ions down towards Earth's poles, where they collide with oxygen atoms to create the massively entertaining and beautiful aurora light spectacles. Now, Mars may not possess a magnetic field, but other planets in the solar system do. Jupiter, Saturn, Uranus, and Neptune each have a magnetic field that is far stronger than Earth's, even though scientists don't understand the underlying mechanisms fully. Venus has a liquid core, but the tardy planet does not spin fast enough to produce a magnetic field. So what is the deal with the magnetic poles reversing? Is it even possible? The answer is yes, and it is known as the Last Champ event or the Last Champ excursion. Spoiler alert, you don't want to be around when it happens. Last Champ event is the name given to geomagnetic disturbance that causes the weakening of the planet's magnetic north and south and the tilting of the magnetic field tilted on its axis, which diminishes the strength to a fraction of its original value. This lessened the magnetic pull that normally directs the flow of high-energy solar particles toward the north and south poles, where they interact with atmospheric gases to illuminate night skies as the northern and southern lights. This happened 41,000 years ago, and it took about 1,300 years for the magnetic field to recover. During that time, the auroras wandered to near equatorial latitudes where they are usually never seen, and the event is not so rare either, relatively speaking. Scientists have discovered that about once every 200,000 to 300,000 years, the field weakens enough to reverse polarity completely. The process can take hundreds or even thousands of years. So how did researchers discover this? The clue comes from magnetic molecules preserved in volcanic deposits and other sediments. They can tell when past magnetic reversals happen because the molecules align with the magnetic field at the time that they were deposited, so they indicate the location of the magnetic North Pole. However, the effects of the Last Champ event were more than the aurora light show's moving bases. In fact, they were dire for organisms alive at that time. A study of bog-preserved kauri trees in northern New Zealand recently revealed the fatal consequences of the Last Champ even thousands of years ago. The scientists cut cross-sections from the preserved ancient trunks and closely examined the changes in levels of carbon-14. Carbon-14 is a radioactive form of carbon that can be used to study ancient materials. What they did was to watch out for the changes in the levels of the carbon-14 over a period that included the Last Champ's reversal. Their analysis showed elevated levels of radioactive carbon in the atmosphere during Last Champs when the magnetic field was weakening. So basically their finding was that the elevated levels of carbon-14 coincided perfectly with records of climactic and biological changes on a terrifying global scale. For example, around this period, megafauna in Australia started declining into extinction, and Neanderthals in Europe were dying out. Their decline may have been accelerated by climate-related happenings to their ecosystems. Computer climate modeling shows that a weak magnetic field, as little as about a 6% reduction of its normal strength, could cause major climate impacts through the ionizing radiation, strongly damaging the ozone layer, letting in UV and altering how the Earth's atmosphere absorbs the sun's energy. Interestingly, further research shows that this period coincided with a shift in cave art by Homo sapiens. Higher UV levels could have driven our ancestors into caves to seek shelter from the harsh sunlight. With plenty of time on their hands while holed up, they simply started to draw and paint on the cave walls. So when will the next magnetic pole reversal occur? There are signs that scientists watch out for, like the North Pole currently migrating across the Bering Sea and the magnetic field degrading by about 10% in the last 170 years, which suggests that another flip might be closer than we think. The flip has happened at least 171 times in the last 71 million years, so we might be due for one. This is why they are racing to understand the phenomenon much more and learn how we can deal with it on a global scale. So what could go wrong today if the Earth's magnetic poles were to reverse? One of the most obvious and painful would be the increase in the rate of cancer cases. Remember, we said the Earth's magnetic field protects us from harmful energetic particles from the sun and cosmic rays. Both of them can cause genetic mutations, so a weakening or temporary loss of the magnetic field before a permanent reversal could increase cancer rates. The danger to life would increase if the flip was preceded by long periods of unstable magnetic behavior. Another effect is the satellites, which are already proving the effect of a weakened magnetic field even though they are in orbit. Already there is a region of the Earth where the magnetic field is about 3 times weaker than at the poles. This spot is found between South America and Africa in the Atlantic Ocean. Researchers call this spot the South Atlantic Anomaly, or SAA. They say satellites in this region consistently suffer electronic failures. Scientists discovered the SAA in the 1950s, and alarmingly, it has since decreased in strength by another 6% while also moving closer to the west. While more research needs to be done, the SAA basically shows us how a weakened magnetic field can affect satellites, as numerous spacecraft have reported electronic malfunctions when flying over this region as they are hit by cosmic rays. Basically, the SAA is like the guinea pig for testing what a magnetic pole flip today would look like, because simulations have been showing features in the SAA spreading globally. Anything that affects our satellites affects us in a critical way. This means our electric grid could be affected and may destroy electronics, including home appliances and wireless devices. The problem is that we have built our critical infrastructure during a time when the Earth's magnetic field was relatively strong and stable, not accounting for events like magnetic poles flipping. So any small variations can spell disaster for the delicate infrastructure that we have built. So you can kiss bye-bye to most of the things you take for granted. No internet, social media, YouTube, mapping direction on your phone or GPS tracker, live broadcast, weather forecasts, environmental monitoring, or communication. You won't even have electricity to power your home. According to experts, the domino effect could cause blackouts that last for decades. Even the rudimentary compass will fail you because it will point in the wrong direction. So good luck to sailors that want to navigate the sea the old-fashioned way. Another effect is behavioral. Some parts of the Earth would be more affected and may become inhabitable. Would this lead to war as more powerful countries try to grab land to relocate their citizens? Even without a catastrophic event like this, some countries try to seize territories belonging to other nations. It remains to be seen how the global community will avoid chaos in this scenario. Plant and animal lives will not be spared either. Even though they do not have sophisticated gadgets like humans, many animals make use of the Earth's magnetic field in different ways, some of which we don't even understand. For example, your pet dog poos in alignment with the Earth's magnetic field, according to a study by Czech and German scientists. They recorded the orientation of dogs' spines while relieving themselves before reaching a conclusion. So you might end up with a dog confused about how to defecate. Lobsters are also known for their large coordinated migrations where they crawl in a single file. Scientists discovered that their sense of orientation is in part based on the Earth's magnetic field. Mole rats, which naturally have poor sight, survive in underground tunnels with the assistance of the Earth's magnetic field, especially on longer journeys. Then there is the popular homing pigeon that will always find its way home. The secret is the Earth's magnetic field. All these animals have what is known as the sense of magnetoreception. One of the accepted theories for this behavior is that these animals have magnetite, a magnetic material in them which allows them to see or visualize the Earth's magnetic field and use it to find their way. The effect of magnetic poles flipping on these animals can already be observed on gray whales that also have the ability to navigate using the magnetic field. On the days with high levels of radio frequency noise caused by solar storms, the Earth experiences abnormally high levels of electromagnetic radiation. When this happens, whales are 4 times more likely to be stranded. It is not like they get the wrong info which confuses their navigation, but these solar storms blind them from seeing magnetic fields. You can imagine the terror that will be unleashed on the animal kingdom as millions, if not billions of animals cannot function normally. But can we as humans prepare for the challenge of an Earth's magnetic pole reversal? The answer is yes, but not a strong yes. Preparation would need to be on a global scale and would require the involvement of all countries. This is complicated by the fact that scientists don't know which parts of the globe would be affected the most. Also, in the era of competing sovereign states' interests, a coordinated response or preparation is almost a pipe dream. Perhaps we will become cave dwellers like our ancestors. Let's hear what you think about the Earth's magnetic pole reversal in the comments section below.